let me start with introducing our first speaker, Pedro Melo. He joined the VASP developer team in 2022. Before that, he was a postdoc at the Condensed Matter and Interfaces Laboratory at the Utrecht University in the Netherlands. His main focus in VASP is to add new solvers for the Bethe-Salpeter equations. You will hear more about these later, and implement algorithms for core-level spectroscopy. Today, he will give an introduction to computing dielectric properties from first principles. Pedro, the stage is yours.
Welcome, everybody. I have the pleasure of opening this VASP workshop on optics and dielectric properties with a lecture on the dielectric function and how it relates to optical measurements. I'll start by defining the macroscopic dielectric function and what properties you can compute from it. Then I'll show how the macroscopic quantities can be linked to the microscopic dynamics through linear response theory, and then what different approximations we can take to study the behavior of the electronic density inside your material. The last section will be spent on how different algorithms within VASP can compute the dielectric function. So, beginning with the dielectric function. We can take definitions from classical electromagnetism and study the response of a material to an external electric field. The simplest case would be for a static uniform field that crosses the whole medium, and we assume that there are bound positive and negative charges, the nuclei and the electron cloud, and when you apply the electric field, the centers of both charges separate, creating dipoles. This lets you define the polarization density as the number of dipole momenta per unit of volume, and with it, you can define the displacement field D as the sum of the external field and the polarization field. Now, if the material in question is linear and homogeneous, but not isotropic, you can write down the following expression for polarization as dependent in first order of the external electric field. And with it, you can express displacement field as only dependent on the external electric field via the macroscopic dielectric constant. But in optical experiments, you do not have static uniform fields. The electric field that you're going to shine on the sample is both time-dependent and might only illuminate a portion of that sample. Not only that, you should consider that the readjustment of the dipole moments is not instantaneous and might have some delay. So in these situations, you can generalize the previous expression to one where the displacement field is linked to the external field by a dielectric function that is both non-local in space and in time. If you apply a Fourier transform and change from real space to reciprocal space, and also if the system allows for time reversal, you arrive at the following relation between D and E, which are now linked by a non-local dynamical microscopic dielectric function. It is with this sort of considerations that we are going to deal in our talk, and we'll learn how to link the macroscopic quantities to microscopic ones. But first, we need to know what properties we can extract from epsilon, the macroscopic dielectric function. Well, if you were to take a monochromatic electric field, aka a laser, and use it in both Maxwell's equations and Ohm's law, you'd be able to define several quantities. First would be the optical conductivity tensor, sigma, for when the external field creates electric currents along certain directions allowed by our system. To the definition of the diffraction index, now a complex quantity, you'd also be able to study how these systems absorb light via the absorption coefficient, which is related to the imaginary part of the diffraction index. You can also study how light is reflected via the reflection coefficient, which is linked to both the real and imaginary part of the diffraction index. As a final example, for magnetic systems, you can study the difference in polarization directions of the incident and the reflected fields, which we call the Kerr angle, and which is linked to the off-diagonal components of epsilon. So, this is the first recap of my lecture. I would like that at this point you keep the following things in mind. First, that the macroscopic dielectric function contains all information about how your system is going to react to an external field. Second, what quantities can be computed from it, but you must now try to figure out how to link the macroscopic function to the microscopic properties, by which I mean how the electronic density and currents inside your material react when perturbed by the external field. To do that, I'd like you to consider how we theoreticians understand an optics experiment. We consider a case where a sample is illuminated by one or more external fields. In the most general case, you'd have both a pump and a probe field. The pump will be responsible for driving the system out of equilibrium, and the probe would then test the configuration of your system at a given delay with respect to the pump. I want to emphasize here that we're only dealing with the regime where only the probe field is active, so there are no excited populations of electrons and holes. So while what I'm going to show you works for quantities like absorption and reflectance, it should not be applied to luminescence experiments, for instance. Now, with only the probe field active, we want to understand how the density N is going to react to a time-dependent external potential. To do that, we consider the following interaction term, H prime, which can be written either in a potential or a density formalism, which are both linked by the following expression. I'm showing you both here in case you find one or the other in scientific papers. Now, following the Green-Kubo theory, we know how to express the first order contribution to the variation of an expectation value of any observable using this expression that is defined via the retarded response function. This function is expressed as the commutator of the operator associated with the observable and the interaction Hamiltonian averaged over the ground state. Why do we take a retarded function? That is to say, why must t be greater than t prime? Well, this is because the response to an external field cannot happen before the field acts on the system. Otherwise, you'd be breaking causality. With this in mind, for the specific case of the electron density, we can write the change in the ground state density given by this expression, and we define chi as the retarded density-density response function. Such a change in density also induces a new contribution to the electric potential, and we follow Coulomb's law to arrive at a relation between the induced potential, chi, and the external potential, where the lowercase v is the instantaneous Coulomb potential. In analogy with what we did for the macroscopic displacement field, we can define the inverse microscopic dielectric function via the following relation between the total potential and external potential. All those expressions together let you define the inverse microscopic dielectric function as a functional derivative of the total potential with respect to the external potential, and also give you an equation for how to compute it, which involves only the Coulomb potential and the density-density response function, which contains all the information on how your density evolves under the external field. So now we have two dielectric functions, one which is microscopic and one which is macroscopic. And we need to know how to relate each other. That is to say, we need to know how to take a macroscopic average. To take this average, we should consider that the wavelength of the external field is usually much larger than the typical size of your unit cells. So if you have a microscopic quantity that you expand in reciprocal space using Q and G vectors, you can take its macroscopic average over all unit cells in this way, which leads to the result that only the G = 0 component is actually contributing to what will be measured. All other elements with G vectors different from 0 do not contribute to the final value. But the external potential is by definition a macroscopic quantity. So you might be tempted to say that the macroscopic average of epsilon is just the microscopic value for which G and G prime are equal to 0. Well, we can show that this is not the case. We start by inverting the equation that links the total and the external potential and look at the contribution to each other, to each Fourier component. For the macroscopic average, only the G = 0 term survives because the external potential is macroscopic, but there is still a sum over G prime left, meaning that you cannot take G and G prime equal to 0. This also serves as a reminder that the average of the product is not the product of the averages. So how do you do it? How do you relate the macroscopic dielectric function to the microscopic one? Well, we look at the original equation for the total potential. We know that inside the sum, only the contribution with G prime equal to 0 survives because the external potential is macroscopic. So when we take the macroscopic average, and by comparison, we define the link between the macroscopic dielectric function, epsilon m, and the microscopic counterpart, which is the inverse of the microscopic dielectric function for which G and G prime are equal to 0. And following the equation in which we relate epsilon minus 1 to V and to chi, we can write this expression. So what is actually inside epsilon naught naught? So this is the macroscopic dielectric function, but without any contributions from local fields. That is to say, contributions from Coulomb interactions from other elements outside of the first Brillouin zone. At this point, it is important from my side to mention that in several cases, you'll not be able to describe all microscopic dynamics using only the density-density response function. If the system has a finite magnetization, you'll have to consider how the microscopic currents will react under an external field. To do so, you have to generalize the interaction Hamiltonian to include the coupling between the external vector potential and the microscopic currents inside your system. However, this is going to mean that your microscopic density and current are going to react to both the external scalar and vector potentials. So your response function is now in fact a 4x4 tensor, where you'll have the scalar density-density response, the vectorial density current or current density response, and finally the matrix current-current response. And in general, all of these functions will mix together and contribute to the dielectric function. But this can be simplified if we fix the gauge of our potentials. Just as a short reminder, both the scalar and the vector potential follow Maxwell's equations and are well-defined up to a gauge function. In solid-state physics, we can take what is known as the transverse or Coulomb's gauge, where the divergence of A is set to 0. This choice is appropriate in cases where we quantize the vector potential, but not the scalar potential, for instance, where the laser is treated in the classical limit as a classical field. Now, with help from Helmholtz's theorem, we know that we can decompose the vector potential into two parts. One which is longitudinal, so goes along K in Fourier space, and another which is transverse, so it's orthogonal to K. But since we had defined that the divergence of the vector potential has to be 0, this means that now the vector potential has no longitudinal component. And the result is that the interaction term in your Hamiltonian, the vector potential will couple only to transverse currents. So the information on transverse response is inside the current, while information on longitudinal response lies inside the density. Since the longitudinal currents are absent from the coupling with the vector potential, we can place them all inside the electric field created by a scalar potential, and we write the following relations for the current, for induced current and density, and define their response to the perturbative field, which is the total field minus the longitudinal induced fields. Now, these two equations, well, 4, since J is actually a vector, let you define a macroscopic dielectric function from the quasi-polarizability tensor. And if we take the arbitrary choice and set the XX direction as the one of the incident field, we can split epsilon into 4 blocks. One which is only longitudinal, transverse longitudinal, a longitudinal transverse, and a transverse block. We have to remark that in general, a longitudinal or transverse perturbation can induce both a longitudinal and transverse response. However, the symmetries of your system can help you. For the specific case where the system has cubic symmetry, for instance, the longitudinal transverse and transverse longitudinal response functions vanish. And it can be shown that for all symmetries, in the limit when Q goes to 0, we can relate the transverse and longitudinal dielectric functions in this way, meaning that in this limit, they have to be equivalent. Final remark, I would like to mention that in some setups, both experimentalists and theoreticians cannot say what direction the light that is being captured corresponds to. So we cannot say exactly if it's XX or XY or YZ or any other possible direction that is being measured, because you do not know the relative orientation of your sample. In those cases, in order to compare with experimental data, you should not look at individual components of epsilon, but at the trace of the matrix. So it's an invariant and will not depend on your orientation. Before I continue, I would like to explain why you are taking the Q to 0 limit. When I started talking about microscopic averages, I mentioned that we are dealing with cases where the wavelength is much larger than the characteristic length of your unit cell. This means that in reciprocal space, the photon's momentum is going to be small when compared to the characteristic momentum of the electrons. Another way to think about this is to consider the implications of momentum and energy conservation laws. So if you're dealing with a semiconductor, the absorbed photon will have its energy and momentum given by these equations. But we also know the dispersion relation for a photon, and we know that the speed of light in atomic units is almost 137. So because the speed of light is so high, to ensure the conservation of momentum and energy, the result is that we have to deal with only vertical transitions when the photon is absorbed. The only way for the momentum of the electron and the hole to differ is if there is another particle involved in the process, which is what happens in cases like phonon-assisted absorption. Now, we are at the end of the second part of my talk. From these last section, I would like you to keep these conclusions in mind. First of all, that the microscopic information is all inside the response function tensor, and that we can link the microscopic dynamics to the macroscopic average by extracting the component with G equal to 0. For all symmetries in the optical limit, both the transverse and the longitudinal responses are equivalent and can be computed from this relation. And for the cases where you cannot isolate the signal from a specific direction, you should look at the trace of the matrix. At this point, we know what quantities we can compute from epsilon and how to link it to the microscopic dynamics. But we still need to know how to describe the changes in the current and the density due to the external potential. Here comes the point at which we must make a choice about the theoretical framework that we are going to use. So some things to consider before choosing though. First is the kind of experiment that we want to study. Does it remove an electron or add an electron, like in photoemission and inverse photoemission? Or does it preserve the number of electrons, like in absorption, but creates an excited state? Also, we should remember that the theory we choose has to be able to describe how a density reacts to a time-varying external potential. So how about density functional theory, DFT? In this case, you have a system of n electrons that is replaced by another of n independent pseudo-electrons that are affected by the Coulomb potential, where all quantities are functionals of the ground state density, and the Coulomb potential is the sum of the external, the Hartree, and the exchange correlation potential. Does this theory fit and obey all the criteria above? Well, it won't take too long to realize that it does not, and in fact, you cannot use DFT to describe optics. First of all, it's a static ground state theory, meaning that it cannot describe excited states. And even if you were to only be interested in energies from transitions between different levels, you'd run into the problem where DFT often underestimates the gap. And so all the energy differences that you compute would be wrong. While this last point, you can address it somewhat by using different and better functionals, the first point is impossible to overcome. However, much like there is a time-independent and a time-dependent Schrödinger equation, there is a time-dependent extension of DFT, which is known as time-dependent density function theory. In this framework, you treat your quantum electrons as evolving under time-dependent exchange correlation and external potentials. All quantities are now a functional of the density, which is also time-dependent. But how do we compute the density-density response function in this framework? Well, we have previously defined the response function as the functional derivative of the density with respect to the external potential, which we are going to name as the reducible response function. But we can also define the response function, a reducible one, where the density reacts to the total effective potential. This last function is actually easy to compute, and as I'll show later, it only depends on the ground state energies and wave functions, which we know how to compute in principle. Now, the only thing we need is to find a relation between both, between the response function that we know how to compute and the one that it's unknown. So to relate them, we employ a chain rule to the definition of the reducible response function and immediately recover chi naught. Now, recalling that the effective potential is the sum of the external plus the Hartree plus the exchange correlation potential, we can employ the chain rule again, but now compute the derivatives with respect to the density. And at the end, we recover again the reducible polarizability, chi, but now we have an interaction term. This is a frequency-dependent kernel that contains all the interactions between electrons and holes in your system. This kernel is given by the sum of the 1/distance instantaneous kernel from the Coulomb interaction and the exchange correlation kernel, which is dependent on the type of functional that you choose. With the previous equations, we can write what is known as the Dyson equation for the polarizability, where at first order, the polarizability is equal to the irreducible one. But now we have a frequency-dependent kernel that will add all interactions between particles, and so will modify chi naught. If we invert both response functions, we can understand what we're trying to introduce with this Dyson equation. The kernel here is expressed as the difference between the known system, given by the irreducible polarizability, and the full interacting but unknown system, given by the reducible polarizability. It involves the Coulomb interaction, but also something which is known as the exchange correlation kernel, which has to be approximated. This exchange correlation kernel is given as the functional derivative of the exchange correlation potential, so it's going to be dependent of the functional of your choice. Now, I want to emphasize that this sort of approach is something that you will be seeing in the next lecture of the school, where the difference between the known system and the unknown system is assumed to be a small correction to be approximated. For instance, if you take adiabatic LDA, the kernel is replaced by a local static function, which is the second order derivative of the exchange correlation energy of the uniform electron gas. Another approximation that you can take is to turn off the exchange correlation contributions from the kernel and keep only the Coulomb interaction. This is known as the random phase approximation. And it leads to the following expression for the inverse dielectric function that depends only on chi naught and the Coulomb potential. This one is often used in models, but more importantly for this workshop, in what are called the GW calculations that you'll learn about in Merzuk Kaltak's talk tomorrow. Now, how does the RPA dielectric function compare to the TDDFT one? Well, we simply apply similar algebra and we would arrive an expression that also only involves the Coulomb potential and chi naught, but now also we have a contribution from the exchange correlation kernel. This means that in either case, we only need VASP to compute chi naught, since the Coulomb kernel is already known, and the exchange correlation part of the kernel is set by the choice of functional before you start your calculation. So in a periodic solid, it was shown by Adler and Weise that you have an expression for chi naught that only involves a sum over several states, both occupied and unoccupied, and which only needs the occupation functions, the DFT energies and orbitals, and the relative weight of your K point. So when running VASP, you should remember that you must set a large value for the variable n bands that ensures convergence over this sum. This might mean that you run into some issues related to the amount of computational resources that you have available because of how different algorithms work when computing the unoccupied states. Namely, the iterative diagonalization algorithm converges very slowly the unoccupied high-lying states, but very rapidly the occupied states. And so the last states will not be converged to the same accuracy. And so in general, we advise that you split your calculations in 2 steps. First, you perform a ground state calculation, and you should note that VASP by default, to accelerate convergence, will add a few empty states. You can check this once your calculation is done in your outcar file by checking for the variables n bands and NLEC. The second step is to compute empty states using exact diagonalization of the Hamiltonian. In this calculation, VASP will keep the number of n bands that you set in your in-car file. You do so by setting ALGO equals exact in your in-car. A word of advice: if your system is extremely large and you need several thousands of bands, setting ALGO to exact can lead to out-of-memory issues. Here you'll have to compromise between accuracy and feasibility, and you should, in principle, try to help it by setting ALGO equal to normal to prevent that your calculation from stopping abruptly due to lack of resources. In your output file, in your outcar, you can check the maximum number of bands that you can compute for a given system by checking for the maximum number of plane waves. Now, regarding the choice of pseudopotentials, you should be using your GW pseudopotentials when computing empty states. This is because these are designed for not only for efficient ground state calculations, and they also must reproduce scattering properties at a large range of energies, which is what you're interested in, since the sum over empty states will force you to reach energy levels high above the lowest unoccupied states. You should also know that the GW potentials have a much higher kinetic energy cutoff, and so a larger number of G vectors is going to be used in your calculation. As a final remark, I would like to emphasize that some elements have different pseudopotentials, and the difference between the files is the number of electrons that is considered as valence electrons, and those which are considered as belonging to the core. So you might need different potentials depending on the material and experiment that you're trying to describe. For instance, if you're trying to describe Kerr measurements where magnetization is important, you should probably consider using pseudopotentials that include the electrons, so that the magnetization is computed accurately. Now, regarding the Dielectric function, VASP will compute both the transverse and longitudinal response functions. They are expressed in this way for the independent particle case, which is the simplest to analyze, but in any other level approximation, you'll be dealing with similar expressions. And in both cases, you will have to converge your summation with respect to these one-centered terms that will show up either in the gradients of the wave functions or their dipolar moments. The essential feature here is how VASP will compute these terms within the projected augmented wave formalism, which revolves around this polarization vector. Now, this polarization vector is how VASP treats the computation of derivatives of the periodic part of your wave function that is associated to the pseudopotential. It is linked to the PAW charge and the dipole tensors in this manner, and it has this expression as a direct consequence of the fact that VASP employs PAW pseudopotentials. If you were, for instance, to consider non-conserving pseudopotentials, you'd find that the polarization vector is simply equal to the cell periodic part derivative in K of the cell periodic part of your wave function. So what algorithms do you have available to compute this polarization vector? Well, VASP has 2 algorithms available. One is done by setting L optics equals true, and it computes the derivative of the periodic part as a sum over unoccupied states. Second option is by setting LPD, that is to say, activating the perturbation expansion after discretization to true. And in this case, VASP will consider a midpoint difference for your derivative and compute your derivative, the derivatives of your wave function using the values after and before. This avoids the sum over empty states by replacing this complete sum here as a midpoint value. Now, there are two final remarks before I finish this section. First of all, I should explain how the Coulomb potential is dealt with inside VASP. This approach is in fact common to many plane wave codes, and it has to deal with the fact that for G equal to 0, the term of the Coulomb potential when Q goes to 0 diverges. And in order to avoid this divergence, whenever it's not possible to take the analytical form of the limit of Q going to 0, we replace the Coulomb potential in this expression by another which ignores divergent term. And we write the macroscopic dielectric function as dependent on the full Coulomb interaction, but now also of chi bar, which is the polarizability computed with all local fields in the kernel when the momentum Q is close to 0. This way, it is possible to avoid divergent terms in all the contributions in the Dyson equation. The last remark before I continue is related to how we interpret the dielectric function, that is, what physical meaning lies behind it. I would like to try to explain what we are trying to describe here when we evaluate the microscopic dielectric function and what it can be used for beyond optics. So think of an electron that is moving through a solid, where there are other electrons and nuclei. When the electron arrives at its new position, it's going to repel the electrons that are nearby, but in its previous position, it will leave a region with a slightly less negative charge, to which nearby electrons can be attracted. Now, all the readjustments are not instantaneous, and there are some retarded effects, so you have to consider that the changes in the medium are dynamical. And so when you either remove an electron, or you create a bound electron-hole pair, you have to consider the effects from other charges in the screening of this Coulomb interaction. This is what we are trying to mimic with a dielectric function, and in fact, the way to do so is to consider that it acts as a screening function over the unscreened Coulomb interaction, and with it, you can define this new function W, which readjusts the strength of your Coulomb terms to account for the dynamical effects of other charges in the material. Now, we are at the end of the third part of my presentation. At this point, I should recall that we can study all microscopic dynamics by using the Dyson equation for chi. And I want to remark that this equation is in fact more general and applies not only to the DFT, but to other frameworks as well. The main difference is how the kernel is approximated, with the TDDFT version being the expression of the functional derivative of the exchange correlation kernel with respect to the density. You should also remember that computing the dielectric function only requires knowledge of the Coulomb, the FXC kernel, as well as chi naught. And that you can turn off the FXC and stay within the random phase approximation if effects from the exchange correlation can in fact be ignored. Again, please keep in mind that in your calculations, you must add a large number of empty states in order to converge chi naught and epsilon. Now, I will go on by introducing some of the algorithms with which VASP computes the dielectric function and the input variables that are important in each case. The first one is when performing a ground state calculation. This is the simplest calculation that gives you a dielectric function and takes the independent particle approximation where chi is equal to chi naught. VASP computes firstly the imaginary part, and then the real part is computed by Kramers-Kronig relation. In the in-car file, you should run a ground state calculation, and you should set L optics equal to true. You should add a sufficiently large number of n bands in order that this sum here converges. And you should set to additional parameter C shift, a small decimal number, usually around 0.1 is enough. And this will deal with the approximations to the delta function and to this eta parameter here, and EE DOS. which deals with the number of frequencies that are added in this integral. Once the calculation is done, you should look for the dielectric function inside the outcar file by searching for these two entries for the density response, or look for this entry if you want to study the current response. The same quantities will also be written inside the VASP.xml file. Just a reminder of what I mentioned before, the normal and exact algorithms which can be used in the ground state calculation are slightly different, in that the normal algorithm uses an iterative scheme, and even though it's robust, the last empty states are not converged to the same accuracy. If you want them to be converged to the same accuracy, you should employ the exact diagonalization of H by setting ALGO to exact. But this is a more expensive algorithm. So another option with which to compute chi-naught is to set ALGO equal to chi, and this one has two methods associated with it. So if you set L spectral equals true, it will split the calculation into two parts. First, it will compute the spectral function of the polarizability, involving only the dipolar moments and the delta function. This and this sum. This is a very efficient sum in that only states where this energy relation is conserved is going to contribute to them. And the delta function is approximated in a way that it's 1 if the energy difference is close to the point on the frequency grid that you are interested in, and 0 if it's close to the points that are adjacent to it. Finally, VASP will replace the computation of the polarizability with this integral by a matrix-matrix multiplication, which means that evaluating it is much more efficient since you can take advantage of fast and highly parallelizable Laplace level 3 routines. In your input file, in your in-car, you should set n omega as number of frequency points and C shift, which again, it will be used to approximate the delta function and deal with the eta parameter that I mentioned before. Now, because of the approximations that we take for the delta function, you don't need to use the same grid for the points that you want to compute the frequency and the frequencies that you are going to use in your integral. So you can have NE DOS different from N omega. And if in your calculation you do see peaks at small frequencies that are spurious, you can remove them away by increase the value of N omega and reduce C shift. This method has another way of computing chi, which is done by setting L spectral to false, and it will evaluate chi directly with no advantages of replacing the sum. So it will evaluate this sum directly. So what are the advantages of each method? Well, if you set L spectral equal to false, you are in principle able to use a small number of frequency points, and this should give you smoother dielectric functions and might require less memory. However, setting L spectral to true is much faster. And you will see in the next lecture how you can use it to compute epsilon within the RPA approximation, which is then going to be used in GW calculations to correct DFT energies. Now, leaving the independent particle approximation, we focus on the inclusion of interactions between electrons and holes. One of the methods VASP has to compute the full Dyson equation for chi is by setting ALGO equal to TDHF. Here we take advantage of the fact that all quantities can be expanded in a particle basis set. What do I mean by this? Well, for instance, looking at the expression from Adler and Weiser for chi-naught, we can realize that it can be written in this way, where chi-naught is now written in an orbital basis. However, we should take some approximations and consider the specific system that we are dealing with. Namely, we are interested in the contributions from G equal to G prime equal to 0, which means that these matrix elements here will reduce to the dipolar moment that we saw before when we look at the expression for the longitudinal response function. Some further approximations are in fact treatments that we can employ when dealing with this matrix is to realize that if we want to study semiconductors at 0 Kelvin, The occupation factors that we see here will either be 0 if it's a conduction state or 1 if it's a valence state. So chi naught will in fact only be 0 if the index n1 is C and index n2 is V, or vice versa, which means that you cannot have both in a conduction state and both in a valence state. The consequence is that we will be studying transitions from valence to conduction, which we call resonant, or conduction to valence, which we call anti-resonant. And since Q is set in the limit of going to 0, we can group the three indices into a transition index, which we call T, and will be responsible for dealing with transition from a valence to a conduction state at a specific K point, or from a conduction to a valence state at a specific K point. And in this notation, this chi naught, instead of having n1, n2, k, will now be with indexes t and t prime for different transitions, and will be dependent on the difference in occupations, which is -1 if it's a conduction to valence or anti-resonant transition, or 1 if it's a valence to conduction or a resonant transition. Now, in this notation, it means that we can write the original Dyson equation in the same transition basis. So when we had chi equals chi naught plus chi naught k times chi, we now expand everything into the same basis that deals only with transitions from valence to conduction or conduction to valence, and we arrive at a matrix equation for the reducible polarizability. And since it's a matrix equation, we can now invert it and arrive at an eigenvalue problem, where you have now this as equal to 0. And the consequence is that in order to build chi, we only need to make sure the determinant of omega minus this auxiliary excitonic Hamiltonian here is 0, which is the equivalent of determining the eigenvalues of this Hamiltonian that deals again with transitions from resonant or anti-resonant case. And because of how it's set up, and we have C to V or V to C at the same K, this Hamiltonian block can in fact be decomposed into 4 blocks. So if both indices are valence to conduction, you deal with the resonant block. If both are conduction to valence, you deal with the anti-resonant. And if one is valence to conduction and the other conduction to valence, you deal with the coupling and vice versa, with the coupling blocks and the resonant and anti-resonant blocks being given by these expressions. So with Hamiltonian now divided into blocks, we can write the eigenvalue equation in this way, which comes from the fact that H is in fact not the emission, and so you have a generalized eigenvalue problem. However, it was shown by Kazida that if you write the problem in a quadratic form, you can reduce the not only the rank of the matrix that you have to deal with. So in this case, instead of the full matrix, you only deal with A minus B or times A plus B, but also now this is an emission matrix, the product of these two. And so you can actually employ routines that deal with emission matrices to compute their eigenvalues and eigenstates. I should remark, however, that in several cases, the coupling element can be set to 0 and you solve only the resonant part of the equation here. And this is called the Tamm-Dunkov approximation. And finally, I should again remind you that despite the simplified notation, the A and B matrices are matrices of rank number of conduction times number of valence times number of K points. So once your hedonic Hamiltonian is decomposed into eigenvalues and eigenstates, you can use this spectral relation and arrive at the interacting dielectric function, where here you have a dipolar moments coupling to the eigenvectors of your excitonic Hamiltonian. How is this done inside VASP? Well, to start with, the approximations to the kernel are controlled by the variables LR3 and LFXC. So if you set both to false, you run the independent particle approximation. And you can use this setup to test your calculations, as the result has to be the same as you obtain when optics is set to true in a ground state run. If you set LR3 to true and LFXC to false, you run the RPA calculation. And if you set LR3 to false and LFXC to true, you run an electron hole interaction with only the exchange correlation elements coming from the kernel only. Finally, if both are set to true, you run a full time-dependent density functional theory calculation. I should remark that for both RPA and TDDFT, you must also set anti-res equal true in the in-car file, otherwise some contributions from the heart rate potential will be missing. And final note is that in order to compare the dielectric function that you can obtain within TDDFT and the one you would obtain with ALGO equal chi, you should set an omega of very large value. Now, much like what was done in the first example, you would require two calculations. First, a ground state calculation with a large number of bands that converges the independent particle epsilon, and with optics set to true, so that the derivatives of the wave function are written in your wave_there file. Second, you run a Casida run by setting ALGO equals TDHF and bands to the same as in previous run, and then you would have to add the flags for LR3 and LFXC. You'd also have to add two very important flags, which is n bands O and n bands V, so the number of occupied and the number of unoccupied states. And I should remark that the first optical transitions happen near the band gap. So you do not need n bands O and n bands V to encompass all the bands that you have set here with n bands. You should stay with a small number of bands near your gap for a semiconductor. The coupling block that I mentioned before can be turned on and off with anti-res variable. So if you set it to 0, it runs the time length of approximation, and this is the default value. If you set it to 1, it will give you the exact results, but only at omega equals 0 frequency. And finally, if you set it to 2, it will run full Casida calculation. At the end of the VASP run, your spectrum will be written inside the VASP run.xml. You should just look for the dielectric function entry in this file. Now, VASP can compute the dielectric function and the TDDFT framework with another interpretation of the dielectric function. It comes from the fact that this expression from epsilon can be written into an operational form, recalling again the spectral representation here. And here you employ a trick. You recognize that this can be written as an integral from 0 to infinity of this exponential. And since the excitonic Hamiltonian is both time independent and does not and will commute with the scalars, you can take it out. And you can understand this as a exponential representation of a time-dependent equation where the initial value is set to this vector. So you would end up having to define a vector, psi, that follows both the time-dependent equation, now evolving under the Hamiltonian with all the excitonic interactions, and that at t equals 0 is set to be equal to the dipolar moments, given by this expression, where Vj is now the velocity operator. If you do all of this, then the macroscopic dielectric function can be written as the Fourier transform of the projections of the initial dipolar moment and its component at each time. So what does VASP do? Well, it will employ a discretization of the time grid and use a recursive solution of the equation to compute the projections of this psi vector with relation to the dipolar moment at each instant. and they will be given by these two equations here. The strategy is similar to what was mentioned before. You first run a ground state calculation, again setting n bands into a large number of bands and with L of x equals true. But now you then run a time-dependent DFT calculation by setting ALGO equals TIMEEV, and you'll have additional flags that you have to set. First is I epsilon, which tells you tells VASP the direction along which to compute the dielectric function, with 1 being x, 2y, 3z, and 4, all of them. And ELM, the number of time steps. And here, if you do not want to use the default, which is 20,000, you should set a value which is larger than 100. And you should also set omega max, so the maximum frequency in electron volt that is going to be used in your integral. So when to choose each algorithm? What are the differences for TDHF and TIMEEV? Well, the standard cases of DFT, so either adiabatic LDA or adiabatic PBE, you'll see that ALGO equals TIMEEV is faster. If you use hybrid calculations, the ALGO equals TDHF is faster and will perform better than the previous run. At the end of either calculation, the VASP run.xml file will contain the dielectric function. Again, you should look for this entry here. Now, I'm almost at the end of my talk. I would like to summarize the different algorithms that we have to compute macroscopic dielectric function. So in case you have no kernel, you can set ALGO equal to normal, equal exact with L of x equals true. There are other algorithms for the ground state. I selected these two for this presentation, but on our webpage you can find others. And you should run first a ground state calculation followed by exact diagonalization, and you should set n bands to a high number in order to converge a dielectric function. And for large systems, you should set with ALGO equals to normal instead of exact in order to ensure that you have enough computational resources to actually run your calculation. If you want to run an RPA calculation, you can set ALGO equals to chi, and you'll have two options, setting L spectra equals to true or false, where true avoids the direct computation of the polarizability using a matrix multiplication, and it's faster. And in the case of setting it to false, you'll perform a direct computation of the polarizability. And while slower, it will require few frequencies and less memory. Finally, within the realm of the full interaction, or either TDDFT or RPA, users of kernel, you have two options within VASP. One is to set ALGO equals TDHF, which will solve the eigenvalue Kazida equation, and which is better suited for when hybrid functions are used. But you also have ALGO equals TIMEEV, which actually employs a time evolution algorithm to propagate the evolution of the dipolar moments, and it's faster when using adiabatic LDA or adiabatic PBE functions. I'm at the end of my talk. I would like to retain the main points of what I've mentioned during this time. So optical properties can be described by the macroscopic dielectric function, which is in turn linked to the microscopic dynamics by the macroscopic average procedure. The accuracy of your results will in fact depend on the theoretical framework that you choose. And DFT is not at all a good framework with which to study optical excitations. And you can, in principle, use TDDFT, which should be able to describe neutral excitations. In the next lectures, you'll learn how to solve both the DFT issue of the incorrect band gaps, and you'll also learn if and when TDDFT can compute optical excitations for each systems, and also when it fails and why. I'll leave you now with some references for all the topics that I've covered during my talk, and I would like to thank you all very much for your attention and wish you happy and successful runs with VASP.
Thank you, Pedro, for the introduction to the fundamentals. I think already at this point it became clear that there are some considerations that have to be taken. Yeah, and I look forward to all the questions that come up amongst the participants after a short break. We will see each other in the Q&A session. Thank you.
Thank you all.